Welcome back to our session. Sorry to cut the conversation, but the clock is ticking and we need to move on. As it was said before, we will have a reduced session with only 4 papers. Hopefully, they are interesting. So we will start with the paper on teaching the significance of numerical model validation with problem-based learning, examples from rock mechanics. The author, Yiouta-Mitra, and that probably I mispronounced it, can't be with us today, so Marina Pantazidou agreed on doing a brief presentation of the paper.
No? Super brief advertisement of the paper, because in some way it answers the question how we check our models. So the way it was presented in the first talk was that many times we can find a hand calculation, but what if we cannot find a hand calculation? So this paper answers this question. So you do validation. This is the importance is on validation, and that's why I would ask you to read the paper. There's only one slide here, and it tells you, okay, go first to see if there are any closed form solutions to do your validation. So the left side is validating your model with an analytical solution, and the right side is validating your case. Of course, this is for teaching with a case study, but if you're the engineer working on the case study, what do you validate your model with? But anyway, in the teaching context, we have 2 ways of validating. I guess in the industry context, we have only one way of validating. So you go and read the paper of my colleague from NTUI. Thank you very much.
Thank you, Marina. We will move on then to the following paper on the role of numerical modeling within a pedagogical framework for soil mechanics courses, implementation for stresses in soils, and this will be presented by Joaquim Macedo.
Thank you, Margarida. Good morning, everyone. I'm presenting this paper that was done with Margarida about numerical modeling within the pedagogical framework that we are developing since some years. So, our motivation. So, basically, our motivation is the preparation for our students and for the challenges of the 21st century. So, our world is changing. It's necessary to prepare the students with other skills, not only technical skills, but also soft skills, and also competences like digital literacy. So we develop a series of teaching and learning strategies that are important in engineering educations because they should encourage active learning to achieve a set of objectives like the deep learning, high-order thinking skills, and also critical thinking. So this study describes the use of numerical modeling to support the teaching and learning in an introductory course of soil mechanics. And especially, we will use the case of stress state in soils to show how we use numerical models to promote deep learning, critical thinking, and digital literacy, while they develop also the technical skills that are so important for their future. So we know from the experience and also from the literature that numerical modeling is important, and it's important to introduce these tools even in the introductory courses. But geotechnical problems are complex problems because they require strong foundations, theoretical foundations. It's important to validate, first calibrate and validate the models because they could give what we want, basically. So their effective use demands understanding of the capabilities and limitations of the tools. And of course, students need to understand the potentialities of the tools and also their risks, like we saw in the talks in the morning. So it's also important to show the physical concepts and demonstrate the physical concepts. So combining physical and numerical models, it's important because it enhances students' engagement, and also promote the conceptual depth of that concepts. So numerical analysis improves problem solving and also reflects real-world engineering practice. And digital tools for foster active learning, critical thinking, and high-order skills that we want to promote in our students. So the context, this is the two programs that we have in the University of Aveiro. In the undergraduate degree, we have basically two courses about sound mechanics, and we have in the first year a course about engineering geology, and in the master a course about foundations and retained structures. We start this path in 2007, 2008, when Bologna process triggered all the change, and we start to create a pedagogical, what we call the pedagogical framework. First, implementing project-based learning in a first model with a cooperative approach, then we evolved to a collaborative approach. Then we start to create new layers of active learning strategies like guided exercises, immediate feedback, flipped learning during the pandemic, and finally, hands-on and team-based learning combined, so experience learning was also implemented. So this framework now it's stabilized, so we have all these active learning strategies combined. Of course, we have formal teaching, we have theoretical practical classes with expositive lectures where we do also simple exercises. We have practical classes where the students solve exercises, and then we have other layers of active learning strategies like hands-on learning where they perform simple experiments. They do also team-based learning, so in some classes we implement this strategy where they collaborate and work in teams to solve some quizzes. And then in the final fundamental, the feedback that is provided by us in big groups. It's important to have independent studies. So we have, of course, the book of Professor Matos Fernandes that we adopt as a reference guide. We also prepare lessons that are implemented in our learning management system, Moodle, where the students can hear some of the lessons that we prepared during the pandemic. And we have the guided exercises where the students solve complex exercises using a step-by-step approach. And finally, the project-based learning where we implemented the numerical models. So they are challenged to solve realistic projects developed in teams, and in the final they receive immediate feedback. So we pick up the topic of stresses in soils, and here we can see how the different strategies are combined and the topics that are studied in this chapter of the syllabus. So for each of the topics, we have different strategies where we try to give to the students different ways to learn the concepts. For example, we start, of course, with the theoretical and practical classes, and in the theoretical practical classes, we solve the more simple exercises, and then we evolve to more complex ones in practical classes, and always giving some real-life cases to illustrate how they have application to reality. In the project-based learning, we usually challenge the students with more complex exercises, where we try to give them two different approaches. One approach where they solve the exercises by hand and using Excel, so spreadsheets, calculations, and we introduce also the numerical models. I give you here some results from the models that the students developed. We use also the GeoStudio. Usually they create simple models because that is the idea. They are undergraduate students. We want to start the use of these models, but we want also to aware the students for the potentialities, but also for the risks, and to dismount also some misconceptions that they have. And also to show them what some, for example, boundary conditions can influence the results. So this is an example of a model that the students developed, and here an example of the analysis that they performed. What is basically the big idea? We challenged students to solve the problem, but most important part, to compare the results. So they compared the results obtained by the two ways. And calculations and spreadsheets, and also the numerical models. They perform critical analysis. So the idea is to compare the results obtained by the two ways and discuss them. And for that is fundamental the feedback sessions. So they discuss the results with us in sessions with one group only. Of course, this is only feasible because we have a small number of students. And in the final, what we want to promote is the development of competences like the deep learning, the critical thinking, and also digital literacy because they are using digital tools. So, to respect my time, some final remarks. So, we implemented numerical modeling successfully in an undergraduate solid mechanics course. We think that all these pedagogical framework foster active, personalized learning, and I think in our opinion, it's fundamental because the students are all different. They need to follow different approaches. Some learn better with one approach, others with other. So the combination of all these different approaches is important for their development. And the skill development is also important. Applied examples support understanding of complex solid mechanics concepts. This is fundamental to show them how the things work. It's important also to encourage autonomy, to promote deep learning, critical thinking, and also digital literacy. And we think this pedagogical framework contributes to that and creates an engaging and supportive environment for academic and also for professional growth that is fundamental for their future lives. Thank you very much.
Thank you, Joaquim. Any questions, comments? Marina, please.
I think it's great that your students have the opportunity to be exposed to numerical modeling in the first course. Do you have later an elective course dedicated for numerical modeling? And if yes, do you teach it? Or if someone else teaches it, do you collaborate with them?
It's a good question. So in our study program, yes, we have one elective course, but it's not working because usually the students doesn't choose the course. So it's prepared. Margarita is responsible for the course, but it's not working because we don't have enough students for that. That is the reason.
Now that you have numerical modeling in the introductory course, you can see a change in this elective.
Yeah, we hope.
Okay, we wish you'd see that different.
Thank you.
Any other questions or comments?
And can you tell us something about the students' feedback about this way of working?
Yeah, the student feedback is very, very good. So they immediately, some of them doesn't show how this changed their future. So, but in the end, and some of them after the course, and for example during the preparation of their dissertations, they tell us that these type of things are important for their growth as students, and also as the tools that they gain to apply in the future. So, for example, during the dissertation preparation, and even some colleagues after the course during the professional life. So the feedback is very, very good.
I will add to that, saying that every time you challenge students out of their comfort zone, they will not be happy. So at first they are not happy, but then they see the value because they see the variety of resources available. They see we do our best to promote their learning, and they really value the feedback sessions. So at the end of each project, we get together with them and we try to address all the errors, misconceptions, and link things to reality. And that makes it really valuable for them.
I will add one thing also. Some of these strategies are implemented in Moodle, so they are totally autonomous. We don't need to give the feedback because the feedback is already programmed in the tool. But that is fundamental. For example, the guided exercises are implemented in that way. So students do the exercises, but they receive immediate feedback if the answer is correct or wrong. And sometimes we give some tips to the students. So they know that they need to lead the textbook in the page or in the section X. And that is fundamental for them because it's an autonomous way to learn. And they need sometimes that because we are not always available to support them. We have other tasks to do. And during the study, that is very, very important.
Any other comment or question? Okay, thank you. Then we'll move on. So the next paper is on integrating advanced computational tools into geotechnical engineering education, an example of transformative learning through digital technology, and will be presented by Ahmed Moghaddasi. Sorry, mispronounced for sure.
Thanks, guys, for coming for my presentation. First of all, my name is Ahmed. I'm coming from Strathclyde University. What I want to describe today is a case study that we did in Strathclyde. We used that case study for a famous course that we have in geotechnical engineering, soil mechanics. So I'm teaching the soil mechanics in Strathclyde, and I try to improve my class. So I found the numerical modeling a way to improve my teaching ability for giving some students some good feedbacks and improving their learning outcome. The first thing which is important for me is why numerical modeling? Why we need numerical modeling in teaching? So we need, in my view, the numerical modeling because we teach a lot theoretical models to students without giving them some viewpoints and feedbacks. For soil mechanics, always we have good theories, we have good understanding of the subject, students learn that, but we never go behind theoretical models. Also, there are a lot of physical experiments that we are doing in soil mechanics. Physical experiments is quite good for students learning, but sometimes it takes time to do the physical experiment. Also, in some universities, it's expensive. You remember during the COVID time, you cannot get access to the laboratory. So those sort of problems we have when we go for a physical experiment. Of course, personally, I believe that we need this, and we need to do it along with the numerical modeling. And finally, simulation allows many difference in design options. So you cannot do instantly the change of the design by using the physical experiment. Maybe the numerical tools will give you opportunity to change parameters, see quickly the result. So all of that is embedded in simulation and numerical modeling. Another aspect which is important for today's presentation, because we are all geotechnical engineering, is why we need digital tools in geotechnical engineering. First of all, students will learn many topics based on problem-solving skills. So we need to define the problems, and then they go for finding some solutions. Also, we need to teach students some real civil engineering projects. What we teach usually in civil engineering was some simple task. We give them some good view of simple task. But in my class, for example, a student asked me a lot of questions about something that I didn't teach them. And I say, okay, forget about this, it's a real situation, you will learn it later. But that later never happens because they need to learn it in the industry, they need to make a lot of mistakes in industry to learn. So giving them some opportunity to try and go finding some errors during the class is important for us. Also, if we teach students some numerical modeling, and that numerical modeling used by many industry, this means that students have some good equipment when they go to the job market. So when you go to job markets, they said, oh, do you know this software? Can you work with other software like this? And most of the kids, students say, no, we will learn it in the industry because university is usually some theoretical background. And finally, if students learn some software which is multidisciplinary, they have some common language to speak with other people. So if you teach them some software that's used by electrical engineering, mechanical engineering, so they can communicate, they can get some drawing from electrical engineering, they can work on that, and they can implement. So picking a good software is important in my view, and we try to pick a good software for our soil mechanics class. What we did was a case study. I use a software. I will tell you what software for modeling of the water flow in the soil. So modeling of the water flow in the soil is a part of geotechnical engineering, and it's part of the soil mechanics. Actually, it's a kind of three-dimensional problems. It's a complex flow in the soil, and it needs some numerical solution. Before using a proper numerical software, I'm teaching this course based on some spreadsheet. So students go to the laboratory. It's kind of the computer laboratory. They go for some hand calculation like this, graphical solution. And in the laboratories, they go for some spreadsheet software like Excel for modeling of the flow. So we did it before any intervention that we had. So in 2023, we had that implementation. We had that flow of the water. Students work on the Excel file, but a lot of complaint coming to me. The complaint was, okay, the spreadsheet was nice, but when I make a mistake somewhere, I didn't know what's wrong with my problems. Another complaint was, okay, this is for two-dimensional problem. What can I do when I go for three-dimensional problem? So those sort of complaints coming from the students. They learn Excel file quickly because it's easy, but they understand that, okay, this is not enough. For real situation, that's not enough. And I agree with them, this is not enough. So I go for a numerical solution in new year, 2024. So instead of using the finite difference method based on Excel file, we use a proper finite element software. Okay, I will give you the name of that, but the key points here is we still have some hand calculation in both years, but we can go for two-dimensional and three-dimensional problems when we are using a proper engineering software. The software that I'm using was ANSYS. So in Strathclyde, we become partner with ANSYS software. It's not that famous in geotechnical engineering area, so it's used in mechanical engineering. But the good point here is it's a general software. It can be used by other engineering as well. And a skill students learn in ANSYS, they can use it later, and they can communicate it with other people as well. A good point about ANSYS is the user interface is very good. So you don't need to teach students too much about the finite element. Also, it has advantage of instant simulation. Many finite element software doesn't have. And it's good for teaching some basic concept to students who doesn't know the finite element. So I found it very relevant for my class. It has a fast visualization, and as I mentioned, it's kind of the multidisciplinary package. The key points about the ANSYS was it's supporting the real-time simulation. Real-time simulation is important because we are dealing with students. Student doesn't have background knowledge about the finite element method. What they know before going to the university was a simple game like this. So they play with a simple game like this. They know how to use their problem solve skills here, but they cannot use it in real situation. So they have this skill already, but we need to give them some opportunity to grow this skill in some useful situation like soil mechanics class. So that's the situation of students. They know this skill. And a good point of ANSYS is you don't need to see about meshing. You don't need to see about time stepping. What you need is to change some parameter. You get instantly some simulation, okay? So I use the ANSYS for my class and for my laboratory. So I changed that laboratory based on the ANSYS. So instead of using the spreadsheet software, I'm using the ANSYS. Students watch a lot of videos in advance, so we create a good quality professional videos in Strathclyde. And in the class, which was the laboratories, they went there, they tried to use the ANSYS by presence of the tutors. So they work on the actual projects of them. And a good point here was we had an extra activity for them based on three-dimensional flow. So in three-dimensional flows, they cannot use any spreadsheet, but what they did in the laboratory was to go for three-dimensional problems. Although this task was optional for them, but many students try to attempt that. And that's a good point for me, because they go for some solution of the real situation. In terms of students' acceptance, we perform a survey, one done by the university and one done by myself. So I did two types of the survey. One is in 2023 and one is for current year. As you can see, the students see that our new strategy is working. So they are more engaged with new material that we put. So they are more happy in 2024. Also, I make a personalized survey, and in personalized survey, I put some questions related to their engagement, etc. What is important here is two questions I highlighted. So the students say that, okay, you did some numerical simulation, that's fantastic, but we still need some physical laboratory. So that's the students' opinion about my implementations. They said, okay, we need this, numerical modeling is good, but we need to do something else. We need to keep the physical modeling as well. Also, they found the ANSYS quite useful, but they said that the training that you provided to us was not enough. So we put some videos, but we didn't prepare a student from the zero knowledge. We just prepared them for that laboratory, okay? What you need to do is to prepare a student from the year one, because they need to see and work with some software, and then gradually we can move on to the year two, year three, etc. I compare their performance in 2 years, 2023 and 2025. The average of the mark was the same between these 2 years, but in the new revised laboratory sessions, I get low mark. So this means that, okay, students like ANSYS, they like numerical simulation, but their mark is low. I'm thinking about the reason for that. I found some clue for that, and maybe it's because we need proper reporting when we go for the numerical simulation. The students submit some work, but it doesn't make sense. They didn't put legends, they didn't put nothing, because they don't know about this. So I'm thinking to improve this in my next teaching round. So this case study, I tried to contact ANSYS, and we put that case study into ANSYS website. So this gives you opportunity, all the educators opportunity, to go and use this strategy for their class. So it's open source area, you can download that. All the steps are here. Our plan is to go further than the soil mechanics class, because soil mechanics is the start of the geotechnical engineering. We need to prepare students for some advanced class, like advanced foundation, geotechnical engineering, etc. Okay? So our plan is to produce some content in year 3, year 4, etc. Out of time, yeah? Okay. Okay. So I'm reaching the, sorry for that. So we get a good satisfaction of students by new intervention that we did. Students found the ANSYS simulation quite useful for their future job career. Also, they found that the physical laboratory, we should keep it. So we cannot put aside the laboratory. So that's not a good strategy. And what I believe is it's good to put some strategy in the year 1. So soil mechanics for us is the year 2. I'm thinking to put some numerical simulation, some basics of the numerical simulation in year 1 as well. So thank you. Thank you.
Thank you. Thank you, Hamed. Questions, comments?
Do you have a version of ANSYS that is specifically prepared for students and that is, you know, simplified for them? Because in general, ANSYS, I don't think is so easy software.
Yeah, thank you. Actually, ANSYS has 2 types of user interface. One is the complex user interface ANSYS Workbench, but they recently launched a new package, ANSYS Discovery. So in the ANSYS Discovery, you don't need to know about the finite element because you cannot see the mesh, you cannot see anything in the background. What you need to put is some boundary condition and pressing start, that's all. And we are using that for students in year 2 because they don't know finite element at all. But anyway, yes, ANSYS Workbench is complex. But we prepare them, we put a lot of video for that, and we try to link students to the ANSYS website for more information, more videos, etc.
Well, I think I have to say that for the benefit of your audience, that you arrived late, and unfortunately, you missed the 2 lectures we had before you. So perhaps because the lectures are videotaped, please watch them, and we can, you know, continue the discussion after you have knowledge of them. It was a big discussion about whether it makes sense to, not big, but it was mentioned, it makes sense to teach the students numerical modeling without exposing them to the underlying mathematics. And from your approach, the answer is clearly yes. So I will ask you the same question to the colleagues from the University of Aveiro. Do you have an elective class later on with numerical modeling? And if the same questions, do you teach it, someone else teaches it, do you work together, all this?
Short answer is no, we don't have it. We have something year 3, but this is year 2 students. They don't know about numerical modeling, finite element modeling at all. But in year 3 even, it's only a numerical modeling, it's not finite element, a numerical modeling in general. What we want to put is something in for master degree, some elective things for master degree. But anyway, I don't think you should expect students to learn finite element in year 1, year 2. They can see, they can play, they can use in a way that they are playing video games. So that's my strategy. But they need to know the theories of, for example, flow of the water in the soil. So we cannot put it aside. We need a benchmark that comparing the numerical solution with that. So we cannot put it aside, in my view.
Can I just reinforce the method? We are not teaching numerical methods. We are using the numerical tool as a virtual laboratory, and we are not downgrading the numerical skill. He is doing the job because he's a numerical person, not me. So the ones who are preparing the tool to be used as a video game by the student has numerical skill and numerical expertise. But that's a virtual laboratory, it's not numerical method. Although we are facilitating later on the approach to numerical method. That is another story.
Thank you, Alessandro.
Any other question or comment? No? So we'll move on. Thank you. Thank you, Ahmed. The next paper is Steady-State Groundwater Flow, combining physical models, hand drawing, and numerical solutions to study plane flow nets. I'll be presenting that, so hopefully I'll be able to check my time and speak at the same time. Having said this, after this morning talks, I want to completely change my talk, but I'll stick to what I had planned and then we'll see how it goes. This has been developed with William Powrie at University of Southampton. We were teaching this together and now I'm doing a similar thing, slightly more complicated, in Aveiro. So every introductory module on soil mechanics includes a part on steady-state groundwater flow, and what we want our students to know is to be able to hand-draw flow nets for a series of different boundary conditions in both confined and unconfined situations, and we want them to be able to use those drawings to calculate pore water pressures, flow rates, and assess stability of, for example, of an excavation floor. Having said this, we need to make sure that they really understand the underlying concepts. So what we've been trying to do is to promote deep learning. And for that, we have drawn into our from our knowledge from different areas. On one hand, the content that we want to teach, but also using pedagogical research literature to inform our teaching. And the paper includes some literature review on that and how to promote effective and deep learning and some strategies that should be used for that, and I won't go into those details now. We also need to address different learning styles. Not everybody is keen on sitting on a room listening to someone talking for hours. So using a variety of resources and of formats can be a way of reaching different students and at different moments. And we also aim to promote visual literacy, so students are able to communicate but also interpret data that is conveyed in a visual format. So for this, what we have been using, and I think this will resonate with Nicola's talk, we've been using a combination of strategies. So we've been using physical models to illustrate the phenomena to students. They then move on to hand-drawing flow nets, and then we use numerical tools, as Francesco said, we're just users, to support all of this, and with two variations that I'll explain later on. So in terms of physical models, we've decided to use a video instead of going into the lab because it's simpler, and we can replay the video, pause. Students can access the video on their own, so they can use it as an element of study to support their work when they're solving exercises, for example. So this is sand and flow around an impermeable curtain. Here you can see some still images of that video. So we have some colored water entering the soil at different moments, so students can visualize the flow lines and the different velocities that we have in different parts of the problem. And in class, I stop the video, I explain, I go back, and I point out different features of the problem. Afterwards, and of course we have formal teaching, explain the theory behind it, we move on to the hand-drawing part. We start by presenting the rules for drawing flow nets, so graphically solving a simpler 2D problem, and we discuss them in class. And then we build slowly and explaining how all the steps link to the rules, a very simple problem similar to the one in the video, so we can relate to that example. And then afterwards, students tackle problems, so they have to hand draw their flow nets in class, even in an environment like this, so they do it on their own, and I walk around helping them to move on. Of course, this is a daunting task. They don't know where to start. So we need to support this in some way. So what we do is we choose a first problem that is quite similar to the one we used to illustrate the topic. We often define the number of flow tubes or equipotential drops that they need to get in their drawings, so they have some reference, and we, as Nicolas was saying, reinforce the idea that they should keep it simple, yeah, to make their life easier. This, of course, evolves, and the flow nets that they need to draw become more complicated, and they include, for example, anisotropy of permeability as well, and both confined and unconfined flow nets. But I won't go into those issues. So then we also use, as I've said before, numerical tools to generate these flow nets. And we do it in two different ways. The first way that we've done at Southampton, and I'm still doing, is we use the numerical tools to generate flow nets that we discuss with students, that we show to students. And the second approach, which is done together with the first, we've been developing at University of Aveiro under the project-based learning that Joaquim presented before, where students also use the software to generate flow nets. Let me see. So under the teacher-led approach, we want to produce educational material, and that includes generating numerical solutions for the problems students are tackling in class, so they have a reference to see, to compare their hand-draw flow nets with, but we also use them to promote in-class discussion, something we've been discussing earlier today. So what's the impact of boundary conditions in the solution? What if we change the soil permeability, the head loss, if we layer the profiles, and so on? So whatever we want to discuss with students, we can. So these are just some examples of the same problems I was referring to before, the hand-drawn and the numerically generated solution. And again, just some examples used in class of flow nets generated for anisotropy of permeability of one soil, stratified soil profile, so we can discuss the influence of the difference in permeability of the two soils, for example, in the solution. So these are just materials that we've generated to support teaching. And some of these have limitations, and we use that for in-class discussion as well. For example, as you can see here on the left-hand side, the boundary is too close to the curtain, and that influences the flow net. So all of this is discussed with students. In class, I ask them to try and explain the differences so they become aware of those. Yeah? And of course, we generate different versions of the flow nets. I think I haven't mentioned which tool I use. I use GeoStudio, as Francesca was mentioned, because I think it's quite user-friendly and for us and for students to use. But GeoStudio doesn't calculate flow lines, it calculates flow vectors. So those flow lines are drawn on top of the equipotential lines, and that can create problems. Yeah? And we, again, discussed that in class, and I often do the exercises of the type spot the error, okay? And this is an example of that. So we point out that flow vectors need to be looked at when using GeoStudio rather than flow lines. So for the student-led approach, as I've said, and I have just a little bit of time, we ask students in Aveiro to tackle team projects. And these team projects are different depending on the topic we are referring to, but they may involve lab work, hand calculations or with spreadsheets and using software. But the key part, as I've said before, is at the end to discuss the outputs with the students, to correct mistakes or demystify misconceptions. All of this work, of course, has to be adequately supported, so we use resources from the software provider, but we've also produced video tutorials fiddling with GeoStudio, generating in different ways the problem, changing the geometry, the boundary conditions, whatever you want, for students to be aware of the impact on the results. And about the meshing, on GeoStudio, we can only change the size of the element, and that is discussed as well with students. So these are just some examples of students' output, hand-drawn and generated with the software from this academic year. And I'm out of time. I would just say that we've tried to use different strategies, and we think this is working. I think we are able to engage students, but at the same time, we foster critical thinking. And I think that's the key part of it. So I would say we can use numerical tools or have students with no background in finite element methods using numerical tools as long as we scaffold that process and support them into their, learning. And I had some more things, but I'll go over that. So as a conclusion, William and I recommend using this variety of tools to support learning. Thank you. So now I'll put my chair hat. Do you have any questions? Thank you, Maria.
Margarida, which one of this variety of tools you will make it open and shareable for other people to use?
Which one of the? Say that again.
You said that we use a variety of tools.
Yeah.
Will you share some of the tools with us? For example, the video?
Yeah, as we've discussed before, I don't own the video. The video was produced at Southampton, so I'm dealing with that to see if we can make it available. So if possible, of course, yes.
Thank you. Thank you, Margarita, for the presentation. How much time do you devote to these combined activities for the topic?
So the full topic, I think it's usually 3 weeks. Of course, the project is done afterwards. So we finish the topic, they are exposed to all these 3 elements, and then they wrap it up while developing the project. And then after their submission, we discuss it straight away.
And so that means that, this is inside the soil mechanics,
yes.
Basic soil mechanics. So 3 weeks plus something else devoted to the groundwater flow. To
groundwater flow, yeah.
Thank you.
How do you encourage your students to do the hand drawings? Because when I've taught this, the endless feedback I get is, please don't ever make me draw a flow net by hand, because I'm never going to do it in industry.
Well, first of all, this is a carrot, yeah? So if it's marked. So if they have to do it in the project, for example, in the test or exam, there will be a flow net, so they need to practice it.
But how do you highlight the value to them of doing it by hand, of the learning process?
In every learning process with students, I think you need to negotiate and do some expectation management. So as long as you show them, as Nicola was saying in the morning, that this is relevant for their profession, we are not just being fussy with them, making them do irrelevant work. They will use it and they will value it later on. We can convince them, but it's, people management somehow, yeah? There's someone back there. They're sitting on the top. But I think we need to move on. Sorry, I'm distracted.
It's just really quickly that I do advise people to draw flow nets when they're comparing with an FE analysis. So you could say that I mean, FE analysis tells you what it tells you. And if you're looking at something involving flow, to understand what it is you're trying to model first off is important, so you can tell your students that. And also tell them the flow nets don't need to be perfect, because I never understood it either.
Fully agree. Yeah. But the thing is to ask them questions. So when they have the 2 solutions, why are they different? What different assumptions have they made? So that's the key part. Do you want to? Because yeah, we do have that? Okay.
I would like to add to the question, Talia. ask you, that was the teaching need I have, not having the simulations, the results you have, is telling students that I'm not asking you to hand draw this, that you will never do it again, and it's nothing, you have nothing to compare to. That later on you will do both the hand draw, the graph, and also the result. But at that point, I have to show them the result, not just tell them that, oh, later on there are some software that produce some results that they look like this. So my question, how much are you going to share? It's not just the video, it's also that comparison of the hand-drawn and the result.
Comparison, it's very dependent on the student's output. So I need to have the student's output and the students with me so we can compare. So I can't just generate a wrong flow net on my own to then discuss the comparison. I'm not sure of being clear, but...
If you remember at the previous conference, we had discussions about how we can handle legally the results of students' work. So your correct result is as valuable as their wrong result.
Yeah, of course.
So if we have this in mind of keeping their work as something useful and something that we can build on and something we can show to future students, of course, that's a lot of work. But
I can add to that often I use wrong students' output or students' outputs with errors to show to the following year, yeah. Or even to create exam questions with wrong flow nets where they need to spot the mistake. So it's a way of doing it. I'm not sure if I fully addressed your question. Yes, Jorge? I'm being questioned.
I do teach my students, when I teach flow nets, they need to hand drawing. And this is an open question. I wonder if we are in the path towards students no longer using the pencil. For example, I also encourage my students to take handwritten notes, and I see my students now taking handwritten notes on a computer. But I don't think that you can draw flow nets on a computer.
They can.
They can?
Yeah, with a tablet and a pen, a digital pen. My students do that, and it's easier than with pencil and paper, because then when they erase, they can have a clean sheet again. So it's much better, to be honest.
So your prediction is that we are going to continue drawing flow nets?
That's what I see at the moment. They all come with their tablets or their computers and hand draw it. David has a question on the back. I'll be here forever. I'm under an oral exam at the moment, yeah? And I don't have ChatGPT to help me.
It's an interesting conversation. So the first of these conferences I went to in Romania many years ago, people were all for getting rid of drawing flow nets. And I made an impassioned plea of the value of flow nets because it's something where the students have to think. And it's one of the rare things where they actually also have to draw. And I think drawing by pencil is actually better than with the iPad, because when you actually erase it, you actually lose the memory, and they need to see the pencil so they can, it actually helps them to draw. So I'm I actually tell my students, don't use an iPad for this. You have to come in with pencil and paper, and if they don't, we send them away. Come back with a pencil.
I have an answer to that. I see your point. Often what I tell them is to save the previous image so they put them side by side so they can improve it, or change the color of the line, for example. Okay, so I think I need to put my chairperson hat, and we need to move on to the next presentation. So we will hear now about short-term versus long-term stability problems in clay, explained through classical figures and finite element calculations, presented by Manuel Matos Fernandes.
Morning to everyone. I am the first author of this paper, and I have the pleasure of collaborating in the paper with my colleague José Borges, that belongs to my university, the University of Porto, Portugal. and as well with Marina Pantasidou from the National Technical University of Athens. Okay. In our basic courses of soil mechanics, the explanation of the soil mechanical behavior is based on the response of small specimens to well-defined and controlled loading conditions in the laboratory. And the loading conditions in the lab are fully drained or fully undrained. And the time-delayed consolidation after loading is treated separately. For those reasons, a closure class presenting field loading, real field loading examples may be highly formative. I'm speaking about the last class of the course, okay? For that closure class, the paper proposes the discussion of these two geotechnical works or geotechnical structures. The construction of an embankment on soft clay and the excavation of a sloped cut in clay. And these two very common and very relevant geotechnical works are splendidly explained in two classical figures developed by Bishop and Bieron, and probably that you know very well. This is the figure for the embankment construction. We see the embankment and the potential rotational failure. The second graph shows the rising of the height of the embankment in time and the rising of the average shear stress on a generic point P of the foundation ground. The increment of the surface loading lead to the rise of the pore pressure. It induces an excess pore pressure over time that reaches the maximum at the end of the construction, and after that we have a consolidation process and the pore pressure returns to the equilibrium. And the last graph is very important. It shows us the safety factor with regard of a rotational failure like this, and we see that the safety factor diminishes during the construction, its minimum at the end of the construction, and increases in time with the consolidation process. Okay? So the next figure is this is the twin figure for the cutting. We see here the evolution of pore pressure. In this case, we have a negative excess pore pressure, okay? The maximum negative pore pressure is reached at the end of the construction, and after that, we have a dissipation of this negative excess pore pressure. The pore pressure increases over time, and this leads to a reduction of the minimum effective stress, a reduction of the shear strength, and a progressive reduction of the safety factor that reduces in comparison with the values at the end of the construction. Here we see two curves for two values of the pore pressure parameter A. A equal to 0 may correspond to an over-consolidated soil, and A equal to 1 to a normally consolidated soil. Okay? So, in my textbook, I introduced a table listing 16 features comparing mechanical and hydraulic phenomenon triggered by the construction of these two works, just a few examples. For example, total mean stress increment. It obviously increases in the embankment and decreases in the cut. Excess pore pressure. It is positive for the embankment and negative for the cut. Soil type in which the excess pore pressure is maximum, normally consolidated, over-consolidated, and another features. So these type of features are related to what happens at a given point of the ground mass. But other features, discuss, for example, the change of the safety factor with time. Okay, it increases for the embankment and decreases for the cuts. The stage appropriated to, it's difficult to control the pointer, the stage for stability analysis. The stability analysis should be performed for the end of construction in the embankments and for the end of consolidation in the cuts, and the conditions for the stability analysis, okay? And according to my experience, is extremely motivating to fill those cells of the table in the class, discussing aspect by aspect with the students, okay, and asking for their collaboration. It's a very well successful class to discuss all this with students aspect by aspect, okay? And this prepares, this creates a positive expectation for the next discipline, that this is a discipline on geotechnical engineering, okay? When we discuss geotechnical structures and not anymore a small specimen in the lab under very simplified and controlled loading conditions, okay? The second part of our paper is a finite element simulation of the construction of an embankment on a soft clay. This was done using a finite element code developed by Borges, by José Borges, that is the second author of the paper. The finite element code that we used as a coupled formulation of the flow and the equilibrium conditions, according to the BO consolidation theory, applied both during the construction and post-construction period. So it can treat the rapid loading, and after that the consolidation process, combining flow and equilibrium equations. The soil constitutive relations are formulated in effective stresses through the PQ theta critical state model, which is an extension of the modified Ken-Clay model. We have here our embankment. It's a small embankment because the clay is very soft. It's a Chicago clay, and the parameters that we have used for the PQ theta model have been extracted from a study of Fino et al. Okay, the thickness of the clay deposit is 25 meters. We have a rigid and impermeable stratum, a superficial crust 4 meters thick, and we have here the typical evolution in depth of the undrained shear strength, okay? So when we use the finite element method, we have an enormous amount of results that we can treat. I will just show 6 slides with the results. This shows the vertical displacements of the ground surface for the end of the construction and the end of the consolidation. okay? We see the typical upward vertical displacements at the side of the embankment, because at the end of construction, volumetric strains are practically null, so the upward lateral displacements must compensate the immediate settlement underneath the embankment, okay? Because globally, the volumetric strain of the ground mass was 0 at the end of the construction. And we can observe after that the end of consolidation, okay? Settlement. Okay, we see here that we have in the center of the embankment an immediate settlement of 15 centimeters, more or less, and further 30 centimeters during the consolidation. Here is the change in time of the midpoint of the settlement of the midpoint of the embankment base. Okay, we see here the 15 centimeters, of the immediate settlement and the time delayed consolidation settlement until reaching the maximum value of 45 centimeters. Okay. This is an interesting result. I hope that I have still some time. No? This shows us the horizontal displacements under the two of the embankment. See the red line. And it's interesting to observe that the horizontal displacements during the consolidation are very small, because in this scale, this corresponds to 2 centimeters, okay? Each square corresponds to 2 centimeters. So we can observe that during consolidation, the horizontal displacements are very small, which is a very well-known result, and that permits to calculate the consolidation settlements using the parameters from the Yiouta-Mitra test, where we have no lateral displacements, okay? Lateral deformations. Here, the evolution of the excess pore pressure, a long time. The consolidation in this case is very long, because the thickness of the clay is very large, 25 meters, and we have an impermeable boundary at the base. Okay? Here we have the safety factor a long time. Okay? And here we have the safety factor at the end of the construction, and its increase over time, and the safety factor is calculated by the slice method, considering for each point of the failure surface the stresses, the normal shear and pore pressure provided by the Feintelment calculations in each Feintelment intersected by the potential, by the slip surface, sorry, okay? So we can observe the increase of the safety factor, and this is the last slide of the results. We can see the critical safety, the critical slip surfaces. That is the slip surfaces with minimum safety factor for the end of construction and the end of the consolidation. And we see that, as we could expect, the critical safety, the critical slip surfaces are not the same. They vary with time, okay? So, I will skip this slide, and as a conclusion, I would say that since the discussion, when considering these two geotechnical works, the embankment on soft clay and the cut on excavated in clay, since the discussion in the class is not anymore restricted to shear strength parameters in the lab controlled conditions, but extends to the resistance and stability of a large soil mass over time, this subject is particularly suitable for an epilogue of a course on soil mechanics, but also as an initial class of an advanced course on soil engineering, or on geotechnical engineering, an initial class. Obviously, if I am speaking of the last class of the basic course, the discussion will be focused on the classical figures and on the table, on the discussion of the table. In the initial class of an advanced course on soil engineering, in a master course, I would say that the discussion might be based on the results of the finite element results, okay, of the finite element computations. Okay, thank you for your attention, and my apologies.
Thank you. Any questions or comments?
So just a question on that. The case study you presented, it's just a predictive exercise. You don't have data to compare the calculations to from performance of an actual embankment? Or?
No, it is not an actual embankment. It is an actual clay mass, but our embankment was an academic example. So we have no results to compare with observation.
Okay.
Okay?
So we need case studies from industry to do that. Yes? Any other question or comment?
Yeah, it's just to say that one of the things I find common, even after people are in the industry, is that they don't really understand that the undrained strength isn't a sort of a unique property. So I think your example really helps illustrate that the undrained strength is a function of the stress conditions, and it's not unique. Whereas if somebody not doing it in the coupled system would decide on some undrained strength they're going to use, and they would do that stability analysis with that undrained strength, and then they would do a drain calculation for the drain case. And it's always, particularly on soft clays, as we all know, incredibly hard to choose an undrained strength, but I think your example is very helpful in illustrating that it's a function of the effective stress parameters and it's not a unique soil parameter. That's what I'm trying to say.
Yes, this is a very important topic of the when we discussed undrained behavior of clays, that the undrained shear strength is not unique, and it is in fact it is one of the most probably the most difficult ideas that we must explain to our students is the concept of undrained shear strength to be used in total stress analysis, but we must emphasize that the value is completely controlled by the effective stresses. So this is a difficulty in classes, and to show that in a real ground mass, the undrained shear strength has an infinite number of values and not a unique value is very formative. Okay.
Any other question or comment?
I have a curiosity. In a starting course of advanced geotechnical engineering, do you compare the result for over-consolidated clays and normally consolidated clays for this embankment, let's say?
For the embankment, no.
For the cuttings? For
the cuttings, because for the embankments, an embankment on a highly over-consolidated soil is not a problem. Okay, in the cut, the difference between the the behavior of a normally consolidated clay and an over-consolidated clay are very relevant and are both a serious problem. So just for the cut, we distinguish.
Also with the numerical methods? With numerical simulations, do you use
well,
numerical for that?
In fact, we do not present in the paper the numerical simulation of a cut, which is much more difficult to perform than the surface loading. Okay.
That's why I was asking.
We are still facing some difficulties with our finite element code to faithfully simulate an excavation, a cut.
Thanks.
So I'll just make a final comment. I learned soil mechanics with Manuel, so I need to acknowledge that. He was my professor, and I use his textbook for my students. So
thank you.
That's thank you very much. And I don't know if you noticed, but I need to point this out as well. 3 Portuguese people presenting in this session, which is also relevant because we are a small country and a small community, so that's interesting as well. I hope the session was useful. Thank you all for attending. We'll have lunch and we'll resume later on. Thank you.